Guys, so we are going to go over the steps to solving a physics problem. This is what I suggest that you do in your separate physics notebook for homework or for notes. These are steps that have really helped me to solve challenging problems when I was a student, and they are just really great tools to put into practice for our class. So the first step, which might seem extraneous, is to actually copy down the entire problem. You can leave out extra words or extra sentences that may not contain pertinent information. They may just set the scene for the word problem. But that really leaves you in a place where you're relying on your ability to dissect the problem. So if you accidentally leave out a sentence that contained critical information, then you won't be using that information to solve your problem. So in the very beginning, I would suggest that you just copy down the problem word for word. So you see here, I've done that with one of your web assigned problems. Number 1, a car travels in a straight line with a velocity of positive 4.5 meters per second. After an acceleration of 0.38 meters per second, the car's velocity is positive 6.5 meters per second. In what time interval did the acceleration occur? So you can see on the right side of the screen, you can see right here that I've imported a picture into my Notability document that's directly from your textbook. So your textbook has organized our kinematic equations into 2 different categories. On the left column, you'll see equations to use when an accelerating object has an initial velocity, meaning it does not start motion from rest. On the right-hand column, all your textbook has done is plug in 0 meters per second for the initial velocity. So those would be the equations to use when an object starts accelerating from rest, where v sub I equals 0. So that's just there for me to reference as I go through this problem. You don't have to do that. You can just split your screen, or you can just have your physics textbook open if you're working with a manual notebook. So the next step after I've copied down the problem is to circle the relevant information for this problem. So I've circled the initial velocity of positive 4.5 meters per second. I've circled the acceleration of 0.38 meters per second. And I've circled the final velocity of 6.5 meters per second. I've also underlined the value that I will be solving for. So in this question, it's asking for the time interval, or delta t. The next step is to organize this data into our list of variables so that I can see what I have and what I'm looking for. So down here, I've labeled all of my given information, v sub I, v sub f, or velocity initial and velocity final, acceleration, and I'll be solving for or looking for delta t, or the time interval over which this motion occurs. My next step is to look over here at the table and to figure out which equation I'll be using. Since I need an equation with both v sub I, v sub f, a, and delta t, I'm going to use the second equation here. So my next step after identifying the equation I'll use is to copy down that equation exactly as it's given. So here I've copied down v sub f equals v sub I plus a times delta t. After I've chosen my equation and copied it down, my next step is to solve the equation in variables for what I am looking for. So I want to end up with an equation that solves for delta t. Just doing some simple algebra, I'm going to isolate delta t. And then in order to solve and plug in actual variables, just for myself, this makes it a lot easier. I'm going to rewrite this equation here with delta t on the left so that it's very clear that I am solving for delta t and plugging in other values. I highly suggest you do this as well. Once I have my equation rewritten so that it is solving for delta t, I can plug in my variables from my table. So here's my table of variables, and I'm going to plug these right into my equation. So I have 6.5 meters per second. as v sub f minus 4.5 meters per second as v sub I divided by acceleration of 0.38 meters per second squared. This gives me a value of 5.26 seconds, which I've boxed. Now there's a couple of ways that you can go ahead and check your work for accuracy. You can either go and plug this delta t back into your equation up above and see if you actually get a v sub f of 6.5 meters per second. So I would take the 5.26 seconds, plug it in for delta t, multiply it by the acceleration of 0.38 meters per second squared, and then add to it the initial velocity of 4.5 meters per second. And if that does in fact yield a v sub f, or a final velocity of 6.5 meters per second, then I know I'm good. Another thing you'll want to do is check the units of your answer. So here I ended up with an answer in seconds, but if I perform the same algebraic calculations right here with just units, meaning without numbers, I can see what unit am I left over with and double check that that is in fact seconds. So in our numerator, we have meters per second minus meters per second, and that's just going to leave me with units of meters per second. In my denominator for acceleration, I have the units of meters per second squared. So really what I have is a complex fraction, or a fraction over a fraction. So that means I have the numerator times 1 over the denominator. 1 over a fraction is actually the reciprocal of that value. So I have meters per second times, and then the reciprocal of meters per second squared, or seconds squared over meters. When I cancel my units, I'm left with the units of seconds, and that is exactly what I got in solving for delta t. So I know I'm pretty good. So here are the steps for solving our physics problem. Number 1, write out the problem and don't cut corners here. Number 2, circle the givens, or circle the information in the problem that will be useful for solving. Number 3 is draw a picture, and for this particular question, drawing a picture wasn't exactly useful for me since I'm looking at a moving object at a different point in time. So I didn't have any kind of distance to label, and it's relatively hard in a picture to label a delta t, and so for myself, drawing a picture wasn't particularly useful, but I would suggest for you, as you're just getting started, to definitely draw a picture. So maybe you have a picture of a car on a straight road, and then further down that road you have the same car, and then maybe you would label delta t with a question mark, and you would label the velocities of the car at those two different instances. Number 4, label and organize the givens, and by givens we mean the information given in the problem. So that would be the table that we made up here of VI, VF, A, and delta t, okay? That's labeling and organizing your givens. Choose your equation. So look at your table and see what equation has all of the things I'm given, as well as the quantity that I'll be solving for. Once you choose your equation, solve the equation first in variables. Do not skip this step. Okay, do not skip this step. It usually accounts for any mistakes in our algebra or in our computing if we just solve it in variables first. It's so much easier to plug in numbers than it is to perform algebra and solve for a variable while the numbers are already embedded in the problem. So do not skip this step. Okay, then you can plug in your values, your actual numeric values, and then check your answer. One more thing I want to point out is please do not enter in data values like positive 4.5 without units. Okay, always enter your units when you're organizing your data, as well as enter your units when you're writing out your calculations. A lot of times mistakes in our organization or possible mistakes in our calculations will stand out to you if you're looking at a problem and you see something with the units that doesn't make sense. For example, if you plugged in 6.5 meters per second, but you have minus 4.5 meters per second squared, okay, that should stand out to you as not making sense. You cannot subtract two quantities with different units. Or say you accidentally plugged in the acceleration value here. Say you have 6.5 meters per second minus 0.38 meters per second squared. That should also stand out to you as being impossible because we cannot add or subtract quantities with different units. Okay, so do not shortchange yourself. Always enter units. Always solve in variables first. It's always better to do more steps in the beginning as you're training yourself to solve these problems than it is to cut corners and miss out on learning opportunities for you to get really good at solving these physics problems, okay? So I look forward to seeing what you guys come up with on our WebAssign assignment, and I really look forward to checking your notebook or looking at your homework notebook when you come in for office hours or at some point during class when you're asking questions. Thanks for watching.